In this problem, we're going to find V0 using nodal analysis. So we'll use our problem-solving strategy on nodal analysis. Note that we have a dependent voltage source in this circuit, and we'll look at how we deal with it. Our problem-solving strategy, the first step says determine the number of nodes. So if we look, we have 1, 2, 3, and 1 node at the bottom. So we have 4 nodes. We're going to select 1 as the reference. Let's pick the bottom one. So that now gives us 3 node voltages. And we will assign them as follows. V1, remember the polarity on V1. V2, the polarity, and then of course V0, we can see the polarity on it. So we have node voltages V1, V2, V0. That means we need 3 equations. And since we have a voltage source, we're going to have a constraint equation for that voltage source, and we're going to have a supernode. And one of our 3 equations will be the constraint equation. So let's write it. So the constraint equation we'll use KVL to get it. We're going to apply KVL around this loop. So we have 4KIX plus V2 minus V1 equal to 0. So then we can write V1 minus V2 is equal to 4KIX. Now, let's go ahead and eliminate IX here. If I look at the circuit here for IX, it turns out in terms of the node voltage is going to be V0 minus V2 over 2K. Okay. So if we look to get that current, we need the voltage with this polarity. That voltage is going to be V0 minus V2. So let's go ahead and make that substitution. So we'll have V1 minus V2, which is 4K times V0 minus V2 over 2K. And this becomes 2V0 minus 2V2. So then, collecting up terms, our equation becomes V1 plus V2 minus 2V0 equals 0. So here's our first equation. So we use that voltage source. We wrote a constraint equation. That gave us one of our 3 equations. For our second equation, we'll apply KCL at this node. Then we'll apply KCL at the supernode to get the third equation. Then we'll be ready to solve. Okay, so again, here's our circuit. We'll show the supernode again and the node voltages. So if we apply KCL at this node, for instance, we'll have a current leaving V0 over 1K. Then we'll have a current leaving this direction. It'll be V0 minus V2 over 2K. And that's equal to a current of 2 milliamps entering. So now if we collect terms, we'll have minus 1 over 2K times V2 plus 1 over 1K plus 1 over 2K times V0 equal to 0.002. Okay, so there's our second equation. Now, we want to do KCL at the supernode to get our third equation. So now I'm going to go through and I'm going to sum currents leaving the supernode through resistance and set that equal to the sum of currents entering from sources. So the first term will be V1 over 3K. Then we'll have V2 over 6K. Then we'll have V2 minus V0 over 2K. And then currents entering from sources, we'll have this one, we'll have 0.008. This one is actually leaving, so entering it's minus 0.002. So collecting up terms in, we'll have 1 over 3K times V1, 1 over 6K plus 1 over 2K times V2 minus 1 over 2K times V0 is equal to 0.006. So there's our third equation. Now we can enter that data or those equations into MATLAB, and if we do that, here's our matrix. So we'll have 1, 1 minus 2, and then our variables are V1, V2, V0. And our second equation is this, and then our KCL equation for the supernode is the following. So now there's our equations for solving using MATLAB. And here's our answers for the node voltages. And here's the voltage that we're looking for, V0.